In this video, we're going to talk about rotations. A rotation is a transformation that is turned about a fixed point, which we call the center of rotation. So when we are rotating an object, there are two things that we need to know. We need to know how much we're rotating it and in what direction. And we also need to know what the center of our rotation is, what the point is that we're rotating around. If the question doesn't specify, then our center of rotation is the origin, the point 0, 0. If it's not the origin, the question would tell you. It will also give you the degree measure that you are rotating by, that you're turning the object by. And if it's not specified which direction, it's assumed to be counterclockwise. If it's clockwise, the question would specifically state clockwise. Otherwise, it is counterclockwise. Couple of things about rotations before we get started. Rotations are rigid motions, so they make congruent figures. And like all congruent figures will have the same angle measurements as each other and the same side length. So after rotation, the pre-image and the image will have congruent angles and congruent side lengths because they will be congruent figures. Rotations do not preserve orientation. As you can see from the smiley face in the image, when you rotate it around the coordinate grid here by different degree measurements, it's facing different directions, not always oriented the same way after a rotation. We do have some rules for rotations, and for rotations, I do like the rules because they make our life a lot easier. For 90 degrees clockwise, which is the same thing as 270 degrees counterclockwise, the rule is that you take your original point, you make your original y coordinate, your original x coordinate the opposite sign, and you switch the order. For 180 degrees, and that's the same in both directions, the rule is that you change the sign of both of your coordinates. Nothing changes with the order, you just change the sign. So that one's a pretty straightforward one. For 270 degrees clockwise, which is the same thing as 90 degrees counterclockwise, you take your original coordinate, you switch the order, and you make the original y coordinate the opposite sign. So it's a little difficult to remember these rules, but they do make your life easier and they will make it super easy to do any rotation because unless you're really good at seeing things visually and seeing where the point's going to end up after you rotate it, it's kind of hard to see how to rotate the figure without the rules. So here I just have a visual on why 90 degrees counterclockwise and 270 degrees clockwise are the same thing. If I take a point and I start in the first quadrant in quadrant 1, and I rotate it 90 degrees counterclockwise, it ends up here in the spot. And that's the same thing as if I would rotate it 270 degrees clockwise, it would end up in the same spot. So that's why 90 degrees counterclockwise and 270 degrees clockwise are the same thing and they use the same rule. They will put an object in the same spot. You can also pause the video and take a look at my visual for why 180 degrees in both directions is the same as each other, and why 270 degrees counterclockwise and 90 degrees clockwise are the same thing as well. What we're going to do now is rotation. So we're going to rotate this figure 90 degrees counterclockwise. Remember, if the question doesn't specify, it's always assumed to be counterclockwise, but here it actually does specify counterclockwise. But if you don't see a direction, that means that it is going to be counterclockwise. So let me take a look at our rule for 90 degrees counterclockwise. So we are going to take our coordinate and we are going to switch the order and make the original y coordinate a different sign. I'm going to take a second and I'm just going to write down the coordinates of each of the points. I'm going to pause the video. Okay, now that I have written down the coordinates of each of my points, it's a lot easier to work with. So the original coordinate j is the point -9. I forgot my negative. That would really change things. 3. So applying the rule, we switch the order, and the original y coordinate will change signs. That would be -3. I should write this a little bit better. My handwriting is so awful. -3 comma, -9. And I'll also graph it so you can see afterwards. -3, 1, 2, 3, -9, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's right here. Okay, let's do the next point, and I'll just label that as J prime. The next point is K. Point K is -7, 8. So the order changes and the original y coordinate will change sign. So that would be -1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. So that would be K prime. Okay, L was -1, 8. So when we switch the order and the original y coordinate changes sign, we have -1, 2, 3, 4, 5, 6, 7. Oh, sorry. -1, 2, 3, 4, 5, 6, 7, 8, -1. So that would be L prime. And then the point M was -3, 3. So that switches the order and the original y coordinate changes sign. 1, 2, 3, 1, 2, 3. And if I connect this together, we have our image, and we were rotating 90 degrees counterclockwise. So if you think about a clock moves in this direction. That's the way that the numbers go. So we know that we were moving in this direction. And since we're moving 90 degrees counterclockwise, centered at the origin, we should expect our figure to move over one quadrant in the counterclockwise direction. So that is exactly where we would expect to go. So the rules do make our life easier. We don't really have to visualize anything, and we can figure out where the stuff goes. Point is only 2 points, so we should be able to do this a little bit quicker. I'm just going to write down the coordinates of point J and K. So this time we're rotating 90 degrees clockwise. So 90 degrees clockwise should put it one quadrant here. So it should put it into quadrant number 4. And remember, 90 degrees clockwise is the same thing as going 270 degrees counterclockwise. So it's the same rule. So I'm going to get my rule. And my rule is that my original coordinate becomes that. So the order switches and the original x coordinate becomes the different sign. So switch the order and the original x coordinate becomes a different sign. Switch the order and the original x coordinate becomes a different sign. And if we do graph it, I know I made a mess of this grid. 2, -1, that's point J prime. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. It's exactly in the quadrant that we expect it to be, so we did rotate it correctly. Okay, moving on. Pause the video and try the next two on your own using the rules for rotations. And you are going to want to pause the video and try it because it's just going to display the answers to you. Here are the answers, so you can pause the video and check your work. Okay, moving on over here, what we're going to do is we're going to figure out what rotation happened. So we can take some of the points and we can see how the points change to figure out which rule was applied. So point P, let me make this a little bit bigger so that I can see this. There we go. Point P is 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. So that's the point 2, 8. And P prime after the rotation is -1, -2, -1, 2, 3, 4, 5, 6, 7, 8. -2, -8. So let's figure out what happened. That is a rotation of 180 degrees. The rule for that is you leave the order of the coordinates the same and you change the signs of the original points. And we can see that also because it did move 2 quadrants over. So this is a rotation of 180 degrees centered at the origin. Moving over to the next one, B is the point -1, -2, 1, 2, 3, 4, 5. And B prime is the point -1, -2, -3, -4, -5, -2. So the order definitely changed here. So let's see how the points changed. So the order changed and the original y coordinate became negative. So the rule that happened here is -y comma x. So this is the rule for a rotation of 90 degrees counterclockwise, and it did move one quadrant over in the counterclockwise direction, or a rotation of 270 degrees clockwise, because we know that that is the same thing and we'll put it in the same spot, centered at the origin. Okay, pause the video and try the next two. If you don't pause the video, it's just going to tell you the answers. Okay, let's take a look at point J. So that is the point -1, 2, 3, 4, 5, 6, 7, 8, -8, 2. I'm going to look at the point J over here. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, so that's not one of our rules. It looks like the distance between J and M actually got bigger. So this would be a dilation. So this is not a rotation. Moving on to the next one. Let's take a look at point E. 1, 2, 1, 2, 3. 1, 2, 3, -2. So let's take a look at what happened here. The order switched and the original x coordinate switched signs. So this is our rule for a rotation of 270 degrees counterclockwise, which would move it 3 quadrants over, so that would put it in the right spot, or a rotation of 90 degrees clockwise, because we know that that is the same thing. Okay, we are going to talk about how to do a rotation if your center of rotation is not the origin. So the best way to go about that is to move it back to the origin by subtracting the point of rotation off of each of your points, doing the rotation the regular way using the rules, and then adding the point of rotation back to each point to put it back to being centered not at the origin. Let's try that out. So I need my 3 points of this triangle, so I'm going to pause the video and just write them down. Okay, so I have my 3 points, and we are not rotating around the origin. We are rotating around the point -1, 1, 2, 3, 4, 5. So we're rotating around this point over here. That's our center. Or if we want to use our rules are specifically only for when we're centered at the origin. So we do have to move each of these points back to being centered at the origin. So the way that we can do that is we can subtract the center of rotation from each of the points. So I'm going to do that first. So if I subtract off, so -1 minus -5 over here, -6 minus -1, that is -5, and 0 minus -5, that is +5. Now we can rotate 90 degrees clockwise. So 90 degrees clockwise is the same thing as 270 counterclockwise. And our rule is that we switch order of the coordinates and make the original x coordinate opposite side. So after we rotate this, the order would switch. So the 5 would come first, but the original x coordinate would switch signs. So since the original x coordinate is negative, it's going to become positive. And after we do our rotation, then we can add the point back. So I'm going to add -1 and add -5. So 5 plus -1, that is 4. And 5 plus -5, that's 0. So the point would be the image point of -6, 0 would be, let me use blue for the image points. 1, 2, 3, 4, 0. So that would be that point right over here. So I'm just going to mark that down. Okay, for the next one, let's center it back at the origin. So I'm going to just subtract the center of rotation from from the point here. 5 minus -1 is 6. 0 minus -5 is 5. I'm going to do the rotation. So I'm going to switch the order of the points, and I'm going to make the original x coordinate a different sign. And then after that, I'm just going to add back the center of rotation because it wasn't really centered at the origin. So 5 plus -1, that is 4. -6 plus -5, that is -11. So that's, let me use blue for this. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. And then finally, our last point over here. So let's subtract our center of rotation. So that would be the same thing as -2 plus 1. So that would be -1. And that would be the same thing as -5 plus 5. So that would be 0. Let's actually do the rotation, switch the order, and make the original x coordinate a different sign. And then after we do the rotation, we can just add back the real center of rotation. So that 0 plus -1 is -1. 1 plus -5 is -4. And there we have it. We plot that, -1, 1, 2, 3, 4. And there we go. That would have been really hard to picture if we didn't use the rules of rotations, especially because we were rotating around a point that was not the origin. Okay, the last thing we're going to talk about in this video is rotational symmetry, which means rotating a figure so that it looks like itself, so that it maps back onto itself. So here we have a pentagon, and it says if it's rotated clockwise around its center, what is the minimum number of degrees to make the pentagon look like itself? So here I have a pentagon just to make it look clearer. And if I rotate this pentagon, so if I start rotating it around its center, notice that it's not matching up exactly to itself. But now it's getting closer to looking like itself, and let's see where it matches up to itself. So that is at 72 degrees. So that's the first time it happens. If we keep going and going, the next time it happens is at 144, which is the next multiple of 72. So each multiple of 72, it'll keep being matched up to itself. So it asks for the minimum number of degrees, so the first time that happens, so that's at 72 degrees. And you can figure that out because 360 divided by the number of sides, which is 5, is 72 degrees. So that works in every situation. The next one is talking about a hexagon, and it asks which measure will carry the hexagon onto itself. So we need to make it look like itself. So we're going to do 360 divided by 6, and that is 60 degrees. But 60 degrees is not here. But remember, any multiple of 60 degrees will work. So I see a multiple of 60 degrees, that's 120. Now we have a decagon, and we want to map the decagon onto itself. So we need to find out which number of degrees could map the decagon onto itself. So let's do 360 divided by 10, because a decagon does have 10 sides, and that is 36. So I'm just looking for a multiple of 36. So 10 is not a multiple of 36. 150 divided by 36, that doesn't work out evenly. 225 divided by 36, that doesn't work out evenly. How about 252 divided by 36? That works out evenly. That goes in 7 times exactly. So that is a multiple of 36. Last question. You might want to pause the video and try it out yourself. Which polygon always has a minimum rotation of 180 degrees about its center to carry it onto itself? So a square, 90 degrees would put it back to itself. So it's not square. That would just be one rotation 90 degrees and it would look the same. Isosceles trapezoid, if we do it 180 degrees, it'll be upside down. It won't look exactly the same. And if we do pentagon, we know that a pentagon from the last question we just did is 72 degrees to get it to look like itself. So rectangle is the answer. If we rotate the rectangle 90 degrees, this rectangle 90 degrees will look like this. But if you rotate it another 90 degrees, which will be 180 degrees, it'll be back to looking like